Okay. Cool. So what we have here, how many of y'all, there's no wrong answer, have looked at the thing that I posted in the Discord?
I'm saying. Someone put me in, I'm going to for right now.
Come on, y'all. I have sent out this link so many times. I will show y'all, I will give y'all the link of the Discord after. It's like the undergraduate Discord. So it has a channel. There's a channel for every single EE class. And it's pretty great. So there's a circuits channel and I put out a good amount of information in there. That would be, actually I have like control over that. So that would be pretty impressive. So there is on that one, it's from Spring 20. There's a Thevenin's question. There is a like steady state complex emittance problem. And then there is a lovely inductor problem. So, and then there's a second order one, which we are going to ignore because it's not on the final exam. Yes.
So there's no second order?
Yes, correct.
We're gonna have, since the second mission had a faster version, we're gonna have inductor issues.
And for the other problems that y'all struggled with. So,
So, how did that, we had that question on the first midterm, where it's like the battery, and you find the minimum of like 12 amps, milliamps first, would it then show that its current source was that?
I have no idea on that one because that's kind of like a special case problem.
Oh, that was kind of a trick question.
Yes, he says that he does not do trick problems.
Let's go.
I agree. He does tricky problems that are hard to solve. But he thinks that that's different.
Like, any trick questions on that? Right?
No. Those are straightforward. Those are just no concepts, know how things work. It doesn't change too much year to year, which is why I can't give away entirely what to study for. And on that note, we don't ever give grades back for final exams, and we don't ever post what it is or the solutions.
You don't post grades.
Not for the final exam. Nobody should. That's kind of,
That's good.
If you could post the grades,
That's a good thing.
like, it's called like.
So we'll find out.
They don't have.
Go within campus.
Little trace.
Have one.
Yeah.
Just for like.
So- mhm. You won't get your grade back for that. You'll just find out if you pass the class or not.
Next semester.
Correct.
Can or cannot.
You cannot. That's kind of school policy. That's not just us. You're not supposed to give final exams back. You're not supposed to give grades back for the final. That's not just us being unreasonable. That's common to basically all of your classes. If they're giving finals back and their grades for the final, that is abnormal. So, promise that's not just us. But part A, just think about things. We've done kind of basic concepts, right? So we've done the idea of conservation of energy. Excuse me. Like conservation of current. So every current going into the node has to leave the node.
Basic laws and principles.
Yes, basic laws and principles, things like that. Like I said, the physics in a very light sense, like not too like insane physics heavy, but like how do things store energy? How do things dissipate things? What's power? Do y'all know the equation for power?
I squared.
I squared R times R.
What is it? I swear I'll only like the two.
No, all.
No, because hypothetically, Ohm's law, right? V equals IR. So if you apply that, then you can replace that voltage in IV by, no, there is no math. There's no math in part A.
Purely conceptual.
Yes. There might be an equation, but there is no numbers.
Mentioned something that we need to know, like the terminology, and so isn't like the terminology he gives us the materials or what he talks in class. Because sometimes you just need to start.
Materials. Uh, yeah, multiple choice, 4 answers for all of them, 4 like choices. Circle one, write it in the, both circle it and write it up at the top. I'm pretty sure it says that in the instructions. And he'll probably say that in class. So do that, move on, don't take more than 15 minutes. Get past part A, move on to part B, basically as quick as you can with still thinking and getting them right if you can. And it's okay. I have,
They take a point, right? But if you answer it and get it wrong,
mhm.
they still take a point, right?
No, it's 0. So you can either gain a point, you can like have a 0 point, like it does not add or lose a point, or if you don't answer it, you lose a point. So like you start at 0, right? If you get a point, you get like 1. So then you might get like, if you get 2 right, you'll have a 2 on the 20 part, like the 20%. But then if you answer 8 right, and then you don't answer 5 of them, then you only have 3 points.
Oh,
It's better off to like go if they know the question.
She'll guess.
Yeah,
So they really don't
Okay.
answer.
yes. Answer something, which is in your favor anyway, because you have a 25% chance to get it right. Cross things off. There's going to be ones that are like, normal test taking strategies. There's going to be ones that you're like, I know it's not this. So cross that out and then choose if you don't know which one is right. I don't grade those parts, by the way. I don't grade part A. He just tells me what the grades everyone gets for part A, and then I finish the calculations. So like he calculates your final grade, but I have the spreadsheet and I give him all the numbers. Yes,
You mentioned, like, he doesn't curve officially.
yes,
right? Let's say for the sake of the argument, right?
yes.
There was some type of curve we don't know about, right? How crazy is that? I'm not- how crazy is that? Curve?
The curve that doesn't exist.
Exactly.
Um,
What's the maximum you've ever seen?
I truly cannot answer that question.
Okay, yeah, that's good.
What's the most people you've seen fail his class?
True.
Oh, yeah.
That's,
That's another way to attack this.
He asked me a real question.
she's like, I'm looking at one.
You're pulling up the big guns.
It's pointed me.
No, last semester, it wasn't like 4 or 5. It was more than that. I'm not going to tell you the exact number. I don't know the exact number off the top of my head. I think it may have been low double digits. But okay,
60 people.
yeah, there was 60 people. But define like the people who didn't get through the class. People got D's more than they got F's. Which isn't like entirely good. But people will ask me, right? Should I even try? A D is so much better for your GPA than an F.
Yeah.
F hurts. So no matter what, if you're scared, try your best, study, and it will help you no matter what. And that's a scary thing, but y'all are gonna get through. You're gonna try your best, and you're here. So, yeah.
Thank-
Any other questions? No more questions? Okay, so the main things we're gonna have is Thevenins, and that's what we're gonna go over today because we didn't really go over that because I ran out of time. And then we'll go next to the inductor problem. So, do we want to start with the inductor problem again, or do we want to go over Thevenin's? Thevenin's is faster. So when you hear Thevenin's, when you look at the word Thevenin's, what should you automatically think? MAME? Nodal analysis, thank you. Those are hard to distinguish. Yes, you should think name. Why is that?
Looking for voltage, definitely knows.
Yep. You want your E Thevenin's. And since now we all of a sudden have a node voltage and a ground, the Thevenin's across from A to B is just equal to this voltage. Can y'all see this? Like, I mean my cursor. Not entirely. What is this? That works. That's actually great. Okay, cool. This is, so that, ouch, it's laggy. I'm sorry. That node voltage is just your E Thevenin's. And then you as well said, now what is our resistance? So V equals IR, right? We know that. We love it. How would we get our resistance? We're going to do our voltage over current. Because of this, we do that weird little J naught. So that is why we're going to add J naught.
No, two.
It's going to be from terminals A to B, where that Thevenin's is. Huh. That's interesting. What do I want to do? Hold on. I'm trying to decide something really quick. If I want to do this one that I just did, or if I want to do this Thevenin's. Let's do this Thevenin's instead. Same exact thing applies, but it's a funkier problem. The other one is a funkier problem, and I want to go over this one first. Is that okay? I want to go over one that isn't super weird. I want to go over one that just does the concepts. And y'all can get comfortable with. Because the other one has a resistor from terminals A to B. And that is a bit strange. And so it makes adding the J naught a little more complicated. Because where would you add it if there's a resistor from A to B? So we're going to do this one first. Yeah, we can. We can. I want to just go over this one first so that we get more comfortable with it. So that we don't get confused. We don't get lost in the sauce. It's okay. You can take a picture of this one. We'll go over it. So stop it. With name, there are, I'm going to say this one more time while y'all write this down. And I said this for the last couple tests, but I highly recommend making a cheat sheet. You get unlimited notes, but I really suggest making something where you can look back and you can say, okay, here are the important things that I should always remember. And this is where you write your like current equation for an inductor. This is where, like, after a long time, like that IL of infinity minus like all of that stuff. Write that down on there. Write down that with name, you're going to look at current sources and node voltages. Write down that Thevenin's uses name, not MAME. Write down all of those things. that are easy to just look at so that you don't have to flip through all of your notes to find like the simple things. There's other little ones too, but that's something that I would highly recommend. So for name, I just told you, what do all of our sources need to be? So we need current sources. So we see immediately that we have these two guys. We need to transform this. And transforming, we need to get really comfortable with because there's probably going to be a source transformation question on there too. I have no idea how he'll make that, if he's going to do a simpler question or if he's going to kind of throw something interesting at y'all, but all source transformations is Ohm's law. That's all it comes down to. Is if you need V, you are going to multiply your current times your resistance. And if you want current, you're going to divide voltage by resistance. Right? That's all source transformations boil down to. And the resistance never changes. Whenever you're doing source transformations, remember the resistance never changes. You should never do anything with it. The value is always the same. The only difference is that whenever you go from voltage in series with the resistance, it is a resistor in parallel with a current source, and then vice versa. So that's that. So let's go ahead and transform this. What is this going to transform into? 3 milliamps, yes. So I'm gonna go ahead and do which way is it gonna be pointing? Yep. Is that plus sign always gonna stay in that same place? And then we'll have the rest of that. I'm gonna move this down. Not gonna, nope, don't do that. Okay. So did y'all have it copied down or do you want me to wait there? Okay. Okay. So we have, stop it. I'm doing the tablet for Teams, but I miss my pen and paper. Then we have 500 ohms there. And we're gonna have this current source. So I'm gonna say the next step that we're gonna do is we're gonna go ahead and write the equation for this guy. So this is gonna be our control parameter equation. So how can we write that equation? Well, let's step back. There are two things in that. So we're going to need to write an equation for I3, and then we're going to need to write an equation for I4. So how do y'all think we can write an equation for I3? Yep. How can we do that? So we got this resistor. And let's actually, I forgot to do this. Let's go ahead and label our nodes. And I think this is something that got a lot of people on the first exam. Labeling meshes and labeling nodes. So, and this is something I don't think we've gone over in this class. You may have gone over it in Turner's class,
Well.
but it was kind of funky.
Right.
Yes.
I feel like part of the groundwork that should have been in the beginning of this class, that was just like, I feel like he thought we just knew that.
You know what? That's really fair. And Turner kind of does this weird thing where he says that every single connection is a node,
Yes, he does.
Yes.
which I adamantly disagree with. And so technically he's right. But whenever you're doing things like mesh analysis or nodal analysis, what they teach in like traditional classes or in the book is that there are like kind of important nodes. And important nodes are defined as where more than two things meet. So like if two things are just directly in series, and this is kind of a visual, but two things are just directly in series, there's a point of connection, but it's not per se an important node. But once there's a third thing, now there's going to be like a current difference. And that's kind of how you can think of it, right? So when two things are just directly connected in series, there's no current change. Whenever it's more than two things, the current is going to split. And that's where we care about KCL. That's where we need to analyze the circuit in that way. So you're going to look for a place where there are more than two connections or more than two things connected, or where current is going to change. So for this, I'm going to go ahead and redraw the whole circuit, and then I think it'll be a little more clear where the nodes are. And then you're always going to have ground, which he did label ground for us. So ground isn't entirely a node. And this is, again, something that's taught in more traditional classes. The amount of nodes that you need for nodal analysis is the amount of nodes that are in the circuit minus 1. And that's because ground. So we always subtract 1 because we have to reference ground somewhere. Because we need somewhere that is a 0 volt place, because everything is within reference to that node. This is all just a construct, essentially. He says that a lot, doesn't he? It's a construct of we need a reference point.
Yes.
Yeah. But how we're going to look at it is we need to find our nodes here. So we know that this whole thing at the bottom is a node, right? All of this down here is all the same, right? There's no difference between any of these things. So this whole thing is considered ground. So I wrote my little ground down there. And then let's look up here. Let's see, I need another color. So let's look up here. We see right here, is there any voltage difference between any of those points? So could we label all of that node 1? Okay, sweet. So now we have VN1. We could, or we could not, if it makes it simpler for you to see, because it didn't change too much. If it helps you to go ahead and combine them, go for it. If it doesn't, just keep it the exact same way it is. So now there's going to be another point where there are more than two things. And this is because we have to remember that this little branch right here is that there's another element, because we need to draw our J naught, right? So we need our J naught, and we're going to connect that from terminals A to B. So we have our little J naught. Now, realistically, it does not matter which way it's pointing. All that it's going to matter which way it's pointing is if at the end you're going to divide by -1 or 1. So you can choose. If you want it pointing in, then you're going to have a positive, essentially, because it's going into that node. And this is, we'll see this later. If you want it pointing down, it's going to be a negative because it's pointing out of that node. So do we want it pointing up or down? Sounds good to me. We're going to have it pointing up. We're going to label this J naught. So now we can see again, it's a little bit more clear where our second node is, right? So this place right here. Is that a node? Okay. We're gonna label as VN2. Are there any other nodes in here? Sweet. So now it's just a 2x2. So even though it's a Thevenin's, it's only a 2x2, which means that the matrix is a lot nicer looking. So now let's go back. I need to label this down. Let's go back and write our I3 and I4 equations. So how can we do that? What's I3? Yep, that is exactly right. So this is because, wait, what did you say?
One minus two. Okay, wait, it's leaving to, on, into one.
Mm-hmm. Sorry, this is I3. Mm-hmm. Voltage is going to go from high to low, which means that the current is flowing that way. So we want it to flow the way it's flowing. That's terrible sounding.
But the rest of the current goes is kind of the opposite, like notation for the voltages.
Mhm.
Yeah, cause I was doing some of these and I got confused that like, it was a little different. When you're writing out what the current is, in terms of like all voltages.
Okay, we can think about it another way too. So let's just erase that. So we know that the current is flowing this way, which means how would y'all feel if I wrote a positive, negative here? So, because we know that wherever current flows into a resistor, it has to be a voltage drop. The resistor is always going to dissipate current. So because of that, we know it has to be a voltage drop, like I just said. So that means that VN1, VN2 is higher than VN1. So because of that, it's going to be VN2 minus VN1. Voltage drop, and that's the way that current's flowing. It all circles around to each other. So I3 is VN2 minus VN1, like you said, all over over 2K. You know, current V over R. Can't forget that resistance. So now let's write it for I4. Or I4 equation going to be. VN2 over 250 ohms. So sweet. Now we have our two equations. We can just go ahead and start writing our matrix. I can fill in the numbers here. So we got 2 milliamps, 2 milliamps. We had 1K here. Y'all need to help me out. What's this? No, the resistor.
Yeah, that was just a problem.
This one is beta.
And that one, 2000.
And this one's 250. One's J naught. Needs a parentheses. Okay. Now we can go ahead and write our matrix.
Three red lines.
We're back. My page was not responding. 3 milliamps. Sweet. So now our matrix. How many resistors, or what is the resistance that is connected to VN1? Sounds right. 3.5K. Now, what about shared between VN1 and VN2? Negative 2K. Same thing down here, right? Negative 2K. And then what about everything touching VN2? Huh? Oh, that's super gross. You're so right. Everything needs to be in Siemens. I got caught up in writing. Thank you. Thank you. So everything needs to be converted. So instead of writing these values here, let's go ahead and switch them. Oh, that's such small numbers. Do we want to convert them numerically, or do we want to just say 1 over all of them? Cool. I like that answer. We could do either. So we can either divide by the current, or we could multiply by the conductance. So either works. So if you have them in Siemens, you gotta multiply. If you have them in ohms, you gotta divide. Which is a great thing to also write with your cheat sheet. Yep, because I is also equal to VG. That's a great thing to write down. So thank you, everybody. Catch them at work. So let's try that again. So we have, do we want to just write them all added? How does that sound? Do we want to just write like 1 over 1K plus 1 over 500 plus 1 over 2K? How's that sound? 1 over 2K, exact same thing, just 1 over. And then what's connected to VN2? We already said that, right? 1 over 2K plus 1 over 250. Okay. This is all multiplied by our VN1 and VN2. So what is this equal to? And are these our current rises or our current drops? Yes. So if it's going into the node, it's positive. If it's coming out of the node, it's negative. Okay. So what do we have on VN1? Oops. No, don't do that. I'm so used to writing IM. Okay. We agree with this? Okay. Now what about VN2? Just J naught. Okay, so let's separate this out into, we're gonna have 3 matrices, right? We're gonna have our independent. We're gonna have our dependent. And we're gonna have, I don't remember what he actually called it. It's our not. our not matrix. Essentially just J naught.
We just call it.
Cool. So what's on our independent? 3 milliamps. And 0. Our dependent. Negative beta, I3 minus I4. And we got 0, 0, and J naught. Sweet. So next we're going to add a page. And then let's go ahead and write out our dependent. So all we gotta do is plug in those values we said up above.
Sure.
So now we're gonna do matrices. We're gonna do negative beta times I3 is VN2 over, what was it, 2K? Yes. Divided by 2K. This is also equal to VN2 minus VN1 times 1 over 2K, which is the same exact thing. So, and then this is going to be minus what was it, VN2 over 250? Sweet. How are we feeling, everybody? Going too fast, too slow? Okay, cool. And then we have 0 down here, right? Big ol' 0. So now the next step is to write this in terms of a conductance matrix times our VN1 matrix. And I've said this before, but if you haven't heard it, the reason we're doing this is because we need to write this in terms of current. We need to be able to subtract the current from the other current. What this means is we need to write the current in terms of the way it's written on the other side. So the other side is also current. We essentially have current is equal to current. It's just written in different ways. So we're going to have a 2 by 2, right? VN1 minus VN2. We're going to have zeros here. We like zeros. So what is the top going to be? Don't forget the 2K. And then over there? Yeah, betas times the whole thing. Okay. And that's a 250. Is that right? Check my work, everybody.
Looks good to me.
Sweet. So now we're going to a big ol' arrow. That's not going to work. And say subtract. Subtract. Because we don't have time for writing out the whole matrix again. Now we're going to have a kind of long 2 by 2. And the nice thing about our calculators is that we don't have to change all of the denominators. We can just put all of the fractions into our calculator and it does all the hard work for us. So help me out. It's rough going back up and down. So what do we got for our first term? And remember, beta was 7, right? So do we want to write it out first, or do we want to put it in the calculator? Actually, let's write it all out first, and then we'll put it in the calculator. So what's our first term?
Correct that now?
Yeah.
1/3.12 minus 7.1 over.
Wait, what? Yeah, we need this whole thing.
Right.
Yeah. You can't just add, you have, it would be like,
Yeah.
yeah, yeah, yeah. Okay. 1/, go back. So 1/1K plus 1/500 plus 1/2K minus beta over 2K. Or minus 7/2K. Is that right? Cool. And then over here, we're gonna have negative 1/2K. Seven over 2K minus 7/250. I wrote that too big. Stop. And then bottom, negative. Okay. Now, what is this equal to? Huh? You're good.
These names. Even. I put anything to change to.
Okay.
Oh, but teenage guys.
So what's our first step? What do we want to find first?
I'll be independent.
No, what does that give us? Well, yeah. Yep. So for V, Thevenin is So our VN you're good. Just
So we're trying to solve, we're getting rid of, J naught.
yes. So for V Thevenin's, for the voltage, we're only going to use the independent sources. So for now, we set J naught equal to 0. So what do we get for our VN1 and VN2? Yeah.
Negative 1.08 for being one and negative 0.12 for being two. The voltage is person two.
Huh?
0.12.
0.12?
Pointed down. Negative one. Yeah.
Okay. No, that's okay. Don't worry.
Yeah, but, when J nine off, be zero.
Mm-hmm.
Okay. What are you gonna do?
Am I tripping? Is that everybody agree? Okay, sweet. So now we are going to find our Thevenin's. So we turn off our independent. So first, let's say what our VN1 and VN2 is equal to. Thank you, everyone with a calculator. So that I don't have to plug it in myself.
What three you want, right? The right there?
Scroll down. Or up. I was like, are you trying to work on the next problem?
No.
Yeah, that's one.
That's definitely not right.
What would be the?
What we replace here versus the 70?
We got zero.
No, you got 0. What would be replaced on 0? 3, 0, and then what would be replaced?
So now what we're doing is we're turning off the independent
Yeah.
and then we turn on J naught. So it's equal to 0, 1.
Yeah.
How did I do that? How did that happen?
Did you get 0? Yes, you got 0, okay. Yeah. It's ideal, but it never happens.
Oh, thank God. Hold on, hold on. Hold on.
That doesn't make sense.
Did we just expect them? It is.
That's about, there's no about.
Yeah, but it just.
I thought myself was this shit, bro. I'm not giving them the. Oh.
Well, it must be messed up on.
I put a large.
On my page, it's not like they're doing it on, like,
Put the Andrew.
Yeah, 200.
Really? Yeah. And still do one night section. Well, that's what I was about to ask. But it's not everyone that can sing.
No.
Okay. He said.
Does he have a different section?
What did y'all, okay, so what did y'all get for the matrix, like simplified, once we did the addition? Did y'all put in all of the addition and then tell me what y'all get for the matrix? For the Siemens one. What does that equal?
I'll just have the matrix.
It's all in. Yeah, hence me asking.
Shouldn't matter. If you have these or not, because you have it or not.
Yes, but I have the answer in Siemens. That shouldn't be zero. Why is it zero?
Zero was how much.
I don't get zero.
Yeah, that's the issue. That's, okay, we totally did this wrong. No, that's, hold up. Am I dumb? I might be dumb.
But in top right should be.
Oh, God.
The negative 7 or. Is that what's wrong?
Mm-hmm.
Yeah, look at all the sketching.
Wait, what?
I never trust.
So,
Yes. So we could. I do. need-
wait, hold on.
How much credit we getting on this? If we do?
This is where I would resolve because so what would happen right now is I would see that everybody is getting the exact same answer and I would resolve Russell's solution and then I would tell Russell that his solution is wrong, which happened on the first exam. Second exam.
An example.
So no, you would have to get the right answer with the problem being wrong.
What voltage did they get?
So, okay, so here's the thing. Try with beta equal to 5. Wait.
What? Why did he use beta for 5? Okay.
Wait,
You said 5?
no, wait, give me a second.
Okay, reading part.
Hold on.
4.
I'll be able to do that.
I can't get much. I'll probably need some. I'll probably get some. Social media, you can send. Yeah, it's like, you know, already. You can't even know what it is, what you need. No, it's fine. You don't know. And it's all possible. Possibility. You don't show up. You need to have. What do you want to do? Yeah, but it's really.
Huh?
Oh.
Oh,
I'm just thinking of Spider-Man.
oh, yeah,
We need a hero.
yeah. Tell me what you get when you use beta as 5. Yeah, so just replace all of the times you see beta with 5. His solutions he solved with beta is equal to 5 for some unknown reason. I think so. So here's what I think happened is he found out that it managed to come out to 0 and he was like, I'm gonna change it to 5, but he didn't tell anybody.
No one would notice. Reason we didn't notice the first time.
See where they pull it all from people, they will have a K in their homes.
Did you get negative 222?
K, kilo ohm or composite, you see, you build like 1/2.
Yeah.
Or you have a 1/K.
Okay.
1/2K. So it's 2,000.
Yeah.
Yeah. Which we did, but I think that everyone's right that it does come out to 0. Yeah. Yep. Try for the voltage.
Okay.
Do the same thing for the voltage. It was just, Russell changed the beta. So everything we did was right, everybody. Sorry. It's okay. So y'all are all lovely, but
He doesn't know trick questions.
no, it's just he had a typo. We all did it right. It was,
It's in a lobby.
no, if y'all put 0, I would have counted it right. Because yeah, no, that's what I'm telling you. I would have resolved it and graded off of what the right answer was. What the like correct. If you solved the equation as it was given, that would be the right answer.
So whenever you're grading,
Yes.
you're not solving these problems from scratch, like, he gives you solutions,
Mm-hmm.
and you verify the solutions, like, he gives you the solution.
Yeah, he gives me the solutions. And then like what happened on the first question for the second midterm, I saw that like some people who definitely like know how to do it and I can look and they did it all right and then they got a different answer from the solution. I like resolve it and I plug the answers that Russell put in the calculator and he just made a calculator error. And so then I grade based on what the right answer should have been.
And these like start over, are these answers he has from years ago?
Yeah, they're old. And so also what happens is people in one semester will tell him, hey, the solution is wrong. And he'll be like, shoot, you're right. And then he'll forget to change it and then upload the same wrong solutions. Yeah. So like there's one that is always, the solution is always wrong. And we know what that right answer is. It's that really weird problem on like the second problem set where like you have to solve for all of the crap, like you have to reduce it down and then bring it all back out.
Yeah.
The solution for that is wrong. Mhm. It's a rough problem,
He found it.
but
That's me a problem.
no. That's one of your homework set problems. No. But we did it wrong. We did it right. He just changed the beta. So if we put beta as 5, the answers that we get are no, it's fine. I'm just gonna go ahead and put so that we don't get 0. Yeah, so our V Thevenins ends up being -1/3. And our what was the other resistance? Was it like 4,000? I think it was 4,000. And then the top one. And then yeah. Okay. Cool. So
Yeah, what's the negative one? Now we're at yeah, so we'll get into zero. We're 20 years. What you're using. Well, yeah. What about zero? Let's say you have zero volts, right? Oh, yeah. What you do is you get a plug in, no one here. Zero about that one.
So there is no. Zero, zero.
I haven't bothered you.
Zero. You just don't know the place.
Okay, also on his solutions, this is, I guess the answer is actually still negative. We are not supposed to divide by -1 because it is positive. Well, we didn't. We divide by 1. Why it's still negative? Is because the problem's weird. And even in his solutions, he says that it's negative. And he'll do this sometimes, and he'll just say, the problem is wrong, and this shouldn't happen in real life, but you solve the problem the way I give it to you, and that's the right answer.
Theoretically, you just want numbers.
Yeah, no, he doesn't like start with the answers and work backwards. So,
Premeditate an answer.
okay. So, how do we feel about that other than the fact that the answer was weird and wrong?
Fine, possibly.
Okay, that's okay. Okay, so let's do a switching problem now.
So the closed circuit just be like upside down first.
Yeah. Yep. Negative, you can either say -1/3 volts and have it pointing up, or you can have it pointing down and say 1/3 volts. Either works, just don't mix them. Don't do pointing down and say negative. Yep. Cool. And then if you divide by -1, I'll take off a couple points, but that's about it. Because it shouldn't have been divided by -1, but that's okay. So, yeah. Yes. Yes. 100%. So, so what we're gonna do to go back over this again. So we have these two. Oh God. Okay, hold on. I'm gonna close it because GoodNotes is being.
Yeah, and you, with probably phone, it's like, what are you gonna come to? Bro, we need like 4 hours. Then you not, this is, you know, I'll do it. I mean, like, we're gonna take a high enough battery. And then that's you, yeah, make the sample. And then make it see, out to a call, once it's totally. I guess the best.
Dang it. Okay. Ark! Okay, guys. So to go over J naught, we see that we have these two. Yes. Okay, that sounds good. We can do that. Here, I wanna.
I need to let it get read.
So,
Hey, over here.
okay. So what you actually do is you take out the load and you just put the J naught instead of the load is what you do. So this is, hey guys, I really would appreciate it if y'all didn't talk while I was talking. Thank you. So what you end up doing for this one is, and I can tell you why. You want the Thevenin's equivalent, right? So what this means is the reduced version of this. That's what we're trying to find. This load, because it's considered a load, we do not want that in our equivalent. That's not included. We use that after. So what we do is we take it out, essentially, for the time being. And then once we find the reduced circuit, we plug it back in. And so we'll eventually, so we put our J naught here. And take that out for the time being. And then once we get it to this, once we get it to here, we plop that load back in, and that's when we solve for this current. So now we're going to have the Thevenin's voltage, the Thevenin's resistance, and then once we complete that circuit with this load, we solve for the current. Does that make sense? Sweet. So now, how do we feel about going to the switch? Sweet. So here is the circuit. And it's going to be similar to how we started. I think one of them, I've looked at so many switch problems recently. But when we first look at this, we're going to see that when the switch is in its first position, we have a voltage source. And then when it's in the second position, we have a current source. Which means if we do want to use name, we can do name on the second part and we can use MAME on the first part. Or we can do voltage divider, or we can do current divider, or we can do anything we want. But with the stipulation that if we chose to do this, or if we do that, we can transform that into a voltage source. But we cannot transform, actually, yes, we can. You know what? There's a lot of ways to solve this. But let's go for it. Thank you. So let's read the question first. First, we're going to calculate the values for the table. And you've seen this table before, including the tau. Next, we're going to generate the full time domain expression. After that, we need to calculate the value of time 1 so that the inductor current is 0, and then the rise time. Right? Sweet. Now we're going to look at this. First step is going to be, we want to find the current at time is equal to 0 minus. So again, what does an inductor look like after a long time? Short circuit, just a wire. So also a great thing to write on your cheat sheet. What does an inductor look like after a long period of time? And then what does it look like right when it switches? So we can go ahead and write this. Let's just draw for time is equal to 0 minus. Let's just redraw this circuit. Oops. Not too bad of a circuit. Pretty manageable. And a wire. And then we're looking for this current. So, conceptual question. Is there going to be any current flowing through this resistor? Because this is a wire, this essentially shorts out this resistor. Because path of least resistance, and these are ideal wires, it's not going to flow through it. It is infinitely higher resistance than 0. So we can actually rewrite this again, where it's just a voltage and a resistor. So now, with that away, what is the current I4? 9/2? Negative 9/2. Yeah, sorry, it was a little rough. Ooh, oh, stop it. Okay, try that again. So now it is negative 9/2 milliamps. Now we can go up here and we're going to go ahead and write negative 9/2 milliamps. Now, what else can we fill in? What else? Yep. I0. What is I0? All right, next step. Let's go ahead and do V4 at time is equal to 0. So once that switch switches, what does this become? It is indeed a current source. So let's go ahead and draw the circuit again. So we have our, we have current source, which way was that current source? Well, I'll do that in a second. I know my resistors are beautiful. So now this one's pointing up, right? So it's 9/2 milliamps. This guy over here is 10 milliamps. This guy down here is 2K. This guy's 1K. And that guy is 3K. And the voltage source is no longer there because it's not connected to anything. Well, it's not closed loop connected to anything. So how do we want to solve this? All right. Yeah, that works. Yep. We want V4.
So I think that's a voltage source.
Oh, maybe you should change it on.
So you'd have to change it back to find the voltage. Or what you would have to do, so do you wanna go ahead and change everything to voltage sources? Sounds good, we can do that. And then we'll go from there. So 10 milliamps, 3K. What do we got? Okay. Yep. Resistor, and then what we got? Now, how would you feel if I said this is now V4? Okay. So now, how can we find that V4 using this? Mm-hmm. Yeah. You have to make sure to add the 4.5 volts.
Yeah.
But yes. Yes. Mm-hmm. So let's see, what is the current flowing? It's gonna yeah. What's the total resistance? And then what's the total voltage? 25.5. Right?
$4.35 million.
So we got, sorry, what was that again?
4.2.
4.25. 4.25 milliamps. So now we need to solve here. So what's the voltage over this 1K? All right, so now what is the voltage V4?
$3.7 before.
Mm-hmm.
Is all that we got.
Mm-hmm. So let's see, we're looking for the voltage drop, right? Is this 4.5 a voltage drop or a voltage rise? From top to bottom? Yeah. So that's why I drew the pluses and minuses so that we see that it's a drop, and then over that voltage source, it's also a drop. And the pluses and minuses can help visualize that. Cause we know, we know that the bottom side is gonna be negative, top side is gonna be plus. We want the pluses and minuses, because we see the voltage at the top. We want top to bottom. That's our voltage drop. If all of the pluses are on the top going to negative, those are all gonna be added. It's only gonna be subtracted if the negatives and positives are flipped. The opposite direction. Now we can come back up here, fill in our 8.75. And now we're going to add, oh, it's not what I asked you to add it.
You see the current.
So our current at time equals 0 is just going to be the exact same as the current as at 0 minus. Yes. So that was what was over the resistor. So the current, if we wanted to find that, we would actually have to do that division here. Because we're looking for the current through this branch. But the current down here is when everything is condensed. Cool? Cool. Yes. Yep. Like superposition for both of the current sources or the voltage sources?
Turn one off.
Yeah. It would take more time, but superposition should always work unless you have a dependent source. Well, you can do superposition with a dependent source, but it's kind of a pain. No, so if it's a voltage source, it's a short circuit. If it's a current source, it's an open circuit. Does that make sense?
How do we get the voltage?
You multiply, or no, you divide the total voltage by the resistance. Sorry, I didn't say that very clear. Yes. Did we? Yes, yes. Sorry, I skipped that a little bit as well. So up here, see how this I4 is pointing that way? So I put in this current source pointing up, so the opposite direction. Yeah, exactly. The moment you flip a switch, just for the people on Teams, the moment you flip a switch, it goes directly correct. It resists change in current. It does not want to change, or you said that. When I said that. Sorry, Brandon said that. It resists change in current, so it acts as a current source. Exactly. Because it acts as a short, because all of the current that's flowing through it is just flowing through it without resistance, which is just a wire. So yeah, sorry about the steps I skipped. I found, yep, I found this current by dividing the total voltage by the total resistance. And then I multiplied the current times the resistance to find 4.25. We know that this one was 4.5 because we converted this into a voltage source. And then we added the two. Are there any more questions on that? Yeah, so see, did you get this part over here where we found the total current? This guy over here. Current.
Okay.
And-
You just won't find what they call it.
Yeah. So now we know the voltage. So one more step. Well, there's actually a couple more steps. Now we just need to find the current at times equal to infinity. How can we do that? We're going to redraw this again with a short circuit instead of a current source. And again, we're looking for this current here. So again, what happens to this resistor? Goodbye. Now, really quick, does everybody understand why? I want to just clarify again. Does everybody understand why that resistor goes away? Yes. So current, we know from current divider, right? The current is going to go through the path of least resistance. More current will always go through the branch where there's less resistance. And we remember from current divider, it's kind of like inversely proportional. So the less resistance, the more current. So if there is no resistance and versus any amount of resistance, is any of that current going to go through the resistor? Exactly. So whenever there is a wire directly in parallel with the resistor, none of the current's going to go through that resistor, which means we can essentially take it out. Yes. Is it directly in parallel? Close enough, not quite. So,
I can understand what I'll say.
Oh, well, it would depend on which resistor goes more.
so you can look at it this another way. So on this wire, let's redraw this really quick. And I'm going to explain why I'm drawing it this way. So we have a resistor, but then we have our other path, right? So we have this path. So how would you feel if I drew the resistor here instead of at the bottom? So now that wire is directly connected in series with that resistor on the bottom. So now it's two resistors in parallel instead of a resistor in parallel with a wire. So yeah, which now I already redrew the next step. So current divider, right? Cool. I need to put in values. That might help. So we have 2K, we have 10 milliamps, and we have 3K. How much current is going to flow here? Let's go ahead and write out the current divider equation. So I in R2, amen. So this, we're going to call this R2 and this R1. So the current in R2 going to equal the total current, so 10 milliamps, times the opposite resistance over both resistors added. So this one's going to be 3K over 3K plus 2K. The other equation for this, and this is the equation that will always work instead of when it's just two branches, is IR2 equal to the total current times 1 over the resistance that you're looking for over 1 over all of the resistance added. Also known as, exactly. So GR2, or yes, over GR1 plus GR2 ... parentheses. So, yes. So if you have 3 branches, you have to use the conductance one, or just write 1 over all of them, which I have a habit of doing.
I was gonna say, the conductance is next one.
That's fair.
Yeah.
Yeah. So the first one is kind of like a quick and fast way to do it. So you know what you're doing. Or we can just always do the conductance one, and that will always work no matter how many you have. So what is the current flowing through there? 6 milliamps. Sweet. So current through L is equal to 6 milliamps. Now we can go write this back up here. And we have, oh, stop it. 6 milliamps. Now we just have one more guy to put in our equation, and that's tau. So how can we find tau? Yes. So what you do is you're going to make essentially terminals where the inductor is. And you're going to say A and B. You don't have to label it that way, but I like doing this because it looks the exact same as everything we've done with resistors. So what we do now is we turn off all the sources. And again, we're going to remember that a turned off voltage source is always a wire, and a turned off current source is always an open circuit. So whenever we find tau, we find it after the switch moves. So whenever we think about that, we're going to say that this is closed and that's not there. And then what we're going to do also, we turn off this guy, which means that it turns into an open circuit. So now when we redraw the circuit, resistor, 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 and terminals A and B, right? So now how do we combine this? Yes. So remember, this is not in series with these two. This guy is not in series. That's not because this terminal and this terminal are connected to other things. So no. So now these two are directly in series with each other. So we can say that it's 3 plus 2. And then that is in parallel with 1K. How's that feel, everybody? Good, shaky? Sweet.
How do you study the art?
Yes. After the switch closes is where your tau comes from. Say that again. Correct. 9 volts isn't there, and that's the reason is because we're trying to develop the steady state equation. So because we're trying to develop it as time moves on from 0, like after the switch, we want the tau after the switch. So if it was the other way around, if we were trying to find the voltage up until time is equal to 0, we would want the other tau. But ultimately, we're looking at as it goes to infinity. So that's where we find the equivalent resistance. Okay, so what is that equal to? 5 in parallel with 1K. Over 6. 5 over 6. 5 over 6. I was gonna say that's just like 2. Five over 6K? Is that how that works? 5 over 6K. So now, what is our tau? I have no idea what the L is. Did anybody write that down? L is equal to 680. Right.
Yes.
Righty.
1/6.
1/6. $116. I'll rewrite it. 816 nanoseconds. So now we can come back up here once again, all the way up here. Do 816 nanoseconds. So now we have part A done. Hooray. Now we need to generate the full complete time domain expression. So what is that going to be? What's the equation? Minus MP negative T over tau plus. So all we got to do, we're going to write that equation and then we're going to plug in our values. So, well, what do we got? Is it IL0 minus? Yeah, it is.
Yeah, it's zero.
Yeah. So it's negative 9 over 2 minus 6. You're right. Divided by 816 nano plus 6 milliamps. Now that's our time domain expression. Sweet. That's it. That's the easy step. You just plug in the values. Yes. Yes. So the way we found tau, we take out this inductor and we put terminals here. Because we want to find the resistance as you're looking in from where the inductor is. So you want to find essentially the equivalent resistance from what the inductor sees. So no matter, go ahead.
So everything.
Mhm.
So everything like between.
No, because we're taking it out. So yeah. So we put, instead of the inductor, we put terminals there. So it's not that we completely take it out. We say looking in, so kind of like a Thevenin's, right? So we're essentially finding the Thevenin's resistance. We find at those terminals, what does that inductor see in terms of resistance? And it's a lot easier when it's on the right, because that's what we always look at. But if it's in the middle, we do the exact same thing. We draw terminals and we say, how can I get the equivalent resistance at those two terminals? How can we reduce it down so that we can see? Talk with my arms a lot. How can we see where that is at those 2 points? So that's all I did. I just redrew the circuit there. Do you see how I redrew the circuit? Okay, sweet. So, and then all we did, we found the resistance, and then tau is just equal to L over R. We have our L, now we have our R, and that's 816 nanoseconds. Cool beans? Sweet. So now the next step is we need to find time T1 where the inductor current is equal to 0. So this is, like I said the other day, we just take this and set it equal to 0. Because we want to know that where, and we solve for T. And this is where I highly recommend having a calculator, because that's a little gross. It's not that bad, but there is room for error. And with a calculator, there's a lot less room for error. So what you do is you do menu 3, 1, and you hit 0 is equal to that equation. And then at the end, you do comma T, and it will solve for T. Yeah. Menu 3, 1 or solve. And then you're going to say 0 is equal to, and then that equation with the T in there. And then at the end, you're going to do comma, and then the variable you want to solve for. So in this case, it's T. And then it'll spit out T is equal to a number. And yeah, if you don't have the TI Inspire, I come rent one. You can have, we have a lot. Well, we have 20, but, and then if you don't have one, I recommend buying one for the rest of your classes here, because they're really, really helpful. Because eventually it also will do complex number calculations. You can do a C solve, which is complex solve. So it'll solve in terms of imaginary numbers, which is great for EMAG. Holy crap, I would be lost without that calculator in EMAG. We all would. So it is an investment in your future, and most people over there will say it is the best purchase we have ever made. Like, I'm just being real. It is. So, time 1, what we got? 6 milliseconds? We agree 6 milliseconds? We getting different, same, somewhere in between? I don't know how you do.
Me and Brenda got this.
No,
What'd you look at?
I can't read.
Oh, we got it. 156, something, somebody who came in. 457 times.
Yeah, same.
We got.
457 nanoseconds. Let's find out.
We got.
Yeah, so time one is equal to 456 nanoseconds. Yeah, that's right. I checked. I have the solutions for this one, which is great.
Helps us.
Oh, wait, reasons.
What did you say, 456, 400?
Wait a minute.
Can't read.
I put
Because it's not.
Okay. So it's not six, it's 456 nanoseconds. So there's a calculator error somewhere for those of you who did not get that. 456 nanoseconds.
Yeah.
Yeah?
Yeah.
456 and some other stuff nanoseconds. Okay.
It's like you're in a negative 10 It's all this.
Oh, that's my fault. But yeah, so then one more thing. Now we got that one done. We got B, we got C. So all we gotta do now is calculate the rise time. What's the rise time? Yep. Easiest equation in this class, right? Tau times ln of 9. Time rise.
Oh, I don't know.
Well, yeah, engineering notation is typically like 456 nanoseconds. That's a nanoseconds. That's terrible. I'm sorry. Nanoseconds. Those 0.416 or 456 micro is the same as 456 nano. So, yeah. Oh, what is it? 1.79 micro. So time right, no, wrong color. Well, you have 2.5. 4.
I can actually read.
I should listen to the press passing or go through those multiple choice in like 20 minutes.
Yeah.
All right. So that's the whole problem.
I got a question at the very beginning.
Go for it.
Which ones could we mark on 0? On the diagram?
Yes. So what does an inductor look like at infinity and 0 or after a long time?
Like the wire.
Is there any voltage over a wire? So what is the voltage at 0 minus?
0. The wire.
Yep. There's voltage at infinity.
Also 0.
Those are the
Or
ones.
it's not a wire. Oh, it's 0.
Yeah, so like, I'm 1.7.
Yeah. So then remember, it changes into a current source at 0, exactly 0. But there's going to be a voltage over a current source.
Yeah, over the.
So that's when it's not 0. Then you have to solve for that. Okay. So, y'all, do we have any questions over that? Do we have anything else we want to go over? I agree. That one's not too bad,
Yeah.
but concepts, make sure your concepts are there. Like I've said, I can give you credit if your concepts are there. I can't give you full credit. But explain to me, write the equations that you use for like part B, C, and D. Right? The fact that you know that time rise is tau ln of 9, right? The fact that you know you have to set your equation equal to 0 to find when the current is equal to 0.
Basically, last 5 minutes, but it's still ready.
Yes.
Right.
If, and like, I can't give you full credit, but if you explain to me exactly what you do, like if you, oh, where'd it go? If you start writing, where is it? There's a very specific thing that I wanted to put down that where did it go?
I'm gonna decide. Like, if I don't know.
If you write this right here, if you write V Thevenin's, you set J naught equal to 0, and then you say it's VN2, even if you don't put in the numbers, that is concept. If you say R Thevenin's, you turn off the independent sources and set J naught equal to 1, and then it's equal to VN2 divided by J naught, that's concepts. That is partial credit. If you were running out of time, write down the steps. Like I said, I can't give you complete credit because numbers are important, but tell me what you want to do, even if you don't have time for it. And also, read through the whole test first. Figure out which ones you know how to do. There will be an easier problem on there. I don't know which one it'll be, but he'll put a problem on there where you know how to solve it. Do that first. Save the hardest problem for last. Yes. No. He said that I think we're there on like this last class. He said everybody did good on that one, so he's not going to put it on there, which understandable. Some people did mess it up. Some people got some of them confused, or they didn't combine it in parallel at the end. No, because that's easy points. Sometimes you need points on the first test.
No, he's like, oh, it's bad. From such an opposite side. I used to always.
The only thing I will say, the only thing he might throw on there, and I'm not making promises, make sure you do remember how to do, yes, inductor or capacitor addition.
Legal.
Just like the.
Combined? No.
Yeah.
And last second district 2 lessons had a capacitance edition, then the final had an inductor edition. That was like easier. Yeah, that's we didn't get any.
Last semester's exams were easier. Yeah. Yes.
So, Dr. Dodd, like, yes, we're behind.
Yes. Yes. So, yes, and write that on your cheat sheet too. Inductors add like resistors, capacitors add like if they were in parallel. So let me say that again. Inductors in series add like resistors in series. Inductors in parallel add like resistors in parallel. Capacitors in series add like resistors in parallel. Capacitors in parallel add like resistors in series. Put that on your cheat sheet. Remember that. Yes. You can. You can. Please just don't like Google stuff. Like, hush. Have your materials downloaded. Please do not pull up Chegg, please. Cause no, please, and here's my thing with that. Here's my thing with that. If we catch you using Chegg, it ruins it for everyone in the future. Don't do that.
Oh, you mean like it won't be open?
It won't be open computer. Once he starts seeing that people are cheating on their computer, he's not gonna let you, no, stop it.
It's also like it's still.
And then we.
No, that's not the point. His materials are useful. Download his materials, but don't be Googling stuff. This is not Turner's 1201. It's not Turner slander. It's just he just
He took 1 credit out right now.
For real? Well.
he just like lets you Google stuff on the final. He's cool. He's great. Dude, he loves my shoes. That was like my favorite thing. He likes comments on my docs, which is great.
Your Bob was fine.
No, Turner School, just 1201, like his exams are literally open everything.
I don't know, it's a whole. The sounds.
Yeah.
Easy, the last thing sounds for the class are like, okay.
Get wrecked.
Okay, you gotta solve this shit.
Yeah, they're a little rough at the end.
Your last assignment you did?
Yeah, that was.
Okay, hold up. The one thing I'm gonna say before I stop the recording, and then we can keep chatting. This up here. This up here. Yes. This will be. Yeah, so it'll be posted. I posted the HKN teams on Canvas. And this is in there. This recording will be in that HKN teams. So you can watch that again and I'll save it on there. I might have someone upload it to YouTube on the HKN YouTube channel. Maybe, but that also is a lot of exporting stuff. A little bit.
Well, if you guys have time.
It's called effectively 6 bit.
No, this one isn't, because the teams, yeah.
So it just makes, it'd just be a video on Teams and it's, it'd just be a video file. And don't need nothing.
Yeah, it just takes a minute to do that.
Have them do it. I'll do it. I used to have a YouTube channel.
Okay, then go for it. But basically, please do not combine these in series. These are in parallel because there is a thing in the middle. There is another thing connected between them.
What is your name?
Oh, no, I just like this. This is like of the resistor combinations. This is what people mess up.
This one, the quiz again.
Yes. Yes.
For only, I think it was the last problem set, like the fourth one.
Hmm.
There was like a question where we had to find tau and it looks like it'd be this, but like way more complex.
Yeah.
We can get into it or
I don't know. I can't tell you that. I don't know. I hope not.
2 hours alone trying to rewrite.
No. What's the Asian guy?
You mean like measure of.
James?
He's
Yeah, yeah.
he's really cheap. His last one.
Yeah.
Kind of
The old one, yeah.
Yeah.
The old, yeah. Yeah, there's 2 Jameses. He's the other James.
Look at that game.
Yeah.
He spent like an hour and a half with videos and like we still kept getting it wrong. And we looked at the solutions he gave us and we're like.
Yeah.
We're
Yeah, so I hope that it's not super duper hard. I cannot promise that. I have not seen it. If it is, like I said, come back to that at the end and tell me the equations for tau, tell me how you would solve it. And
we didn't solve.
well, try.
Well, yeah, let's see, try.
If you just write the equation, it's if you write the equation using your numbers and like you tried to solve it, it's a little more. Yeah, Yes,
Do you remember last semester, we had second order on final?
you did not.
So we're on second order this one?
You are not having second order on the final. And if he lies again, I'm gonna go find his house or something.
Yeah, I already.
I'm prepared for second. I'm prepared.
I'm gonna answer the foundation.
Oh my gosh.
What's some people about digital?
Okay, I'm gonna stop the recording. Bye, y'all. This will be uploaded. But yeah, are there any more? Are there any more questions from y'all online?
Like and subscribe. There's only 4 people.
It was like 7, I think. We had like the Avengers Assemble.
Was the solutions number 2? I'm gonna upload the solutions to that midterm that I posted. I wanted to let y'all kind of simmer on it and solve it before you just go straight to the solutions, which I understand. I wanted you all just kind of pick at it first. So I'm gonna upload it on the Discord as well. And then I will give y'all the link to the Discord if you're not in it. Yeah. 60-ish,
I could drop.
60-ish. I haven't counted. 60-ish. I'm gonna stop sharing. I'm gonna stop recording.
Those funny digital.